Wave-particle duality is a key concept in modern physics, which explains that light and matter can behave as both wave and particle. In classical physics, wave and particle were considered completely different, but experiments at the microscopic level show that this is not always true. This dual behavior is clearly shown through several important experiments. The first experiment is that the photoelectric effect demonstrates the particle nature of light, where light transfers energy in the form of photon to release electron from a metal surface. The concept of matter wave proposed by de Broglie shows that particles such as electron can behave like wave. In addition, experiments such as electron diffraction or the double slit experiment provide direct evidence of wave-like behavior in particles. By studying these three experiments, we can better understand how light and matter exhibit wave-particle duality. Each experiment highlights a different aspect of this concept and helps explain the behavior of matter at the atomic and subatomic level.
Up until this point, the scientific community, largely following Isaac Newton, was convinced that light was made of tiny corpuscles or particles, but there was strange behavior like exhibit that particles just couldn't explain. To understand duality, we have to look at what happened in 1801. Thomas Young performed an experiment that seemed to settle the debate forever. To understand duality, we start with the classical proof of waves. In 1801, Thomas Young devised this experiment. Look at how the light leaves our source as a simple wave. As the light hits the two slits, it diffracts and overlaps. Notice the interference occurring in the middle. This is the heart of wave physics. On the detector, we see many bright and dark stripes. The bright areas are where wave peaks meet, creating constructive interference. The dark gaps are destructive interference. If light were just particles, we would only see two spots, but here we see a wave pattern.
Classical physics predicted that if we just make light bright enough, it would eventually kick out electrons. But look, even with maximum brightness, these low energy red photons just bounce off. They don't have the individual energy to break the electron bonds. Now, watch what happens when we increase the frequency to blue or violet. Suddenly, even at low brightness, electrons are being ejected. This is because light travels in a packet called photons. It only takes one photon with enough energy to free one electron. As we increase the frequency further, notice how much faster the electrons fly. The extra energy from the photon becomes the kinetic energy of the electron. This is Einstein's famous photoelectric equation in action.
Now about matter wave. Matter wave comes from an idea proposed by Louis de Broglie. He suggested that particles, such as electrons, can behave like wave, just as light can behave like both a wave and a particle. This concept is known as wave-particle duality. It shows that in the microscopic world, matters do not follow only classical rules. De Broglie idea acts as a bridge between classical physics and quantum physics. Classical physics describes large objects, while quantum physics explains that the behavior of very small particles. Because of this connection, the concept is often called the de Broglie. See how a solid object can suddenly turn into a ripple? Let's take a look at this animation of matter wave to understand more. Here, we are firing electrons one at a time. In classical physics, an electron is a solid particle, a tiny ball of matter. If you watch them leave the gun, they look like dots. But as they pass through these two slits, something impossible happens. Each individual electron behaves like a wave. It doesn't choose slit A or slit B. Instead, it exists in superposition, acting as a wave or probability that travels through both. Watch the detector screen on the right. As the heat accumulates, they don't form two parts. They build up the interference pattern we previously only saw with light wave. This confirms de Broglie genius matter inside has a wave nature. This proof at the quantum level, the distinction between solid and a wave disappeared. But what happens if we try to slit at a speed which slit the electron actually used? That is the final mystery. Many people think quantum mechanics is only something we study in textbook, but in reality, we use wave-particle duality in our everyday life without even realizing it. Many modern technologies today work because particle can behave like a wave and wave can behave like particle. Let's look at the electron microscope. Ordinary light microscopes are limited because light has a relatively long wavelength, so they cannot see extremely small objects like virus or atom. Electrons, however, have a wave property with a much shorter wavelength. Because of this wave nature of electron microscope can magnify objects up to 1,000 times smaller, allowing us to see the nanoworld. Next, consider solar panel. Solar panel work based on the photoelectric effect, which was explained by Albert Einstein. Here, light behaves like a particle called photon. When this photon hit the silicon surface, then no electron loose, producing an electron current. This shows the particle nature of light in a real-life application. Another important example is a laser technology. Lasers rely on quantum transition and wave behavior of light. The waves are coherent, meaning they move in phase, producing a very focused and powerful beam. This is why lasers are used in surgery, barcode scanner, fiber optic communication, and many modern devices. In conclusion, from electron microscope and solar panel to laser in internet cable and smartphone, wave-particle duality is not just a theory, it is the silent engine driving modern technology in the 21st century.
So in summary, quantum mechanics show us that one particles can exist in two realities. Experiments like Young's double slit and the photoelectric effect prove that the particles can behave as waves or as particles, while de Broglie connects the both ideas into a single framework. This means the paradox is not a mistake in physics but a limitation of how we observe nature. The behavior we see depends on how we choose to